welcome back. In this video, we're going to illustrate the Rolle's theorem for a given function. So essentially, we are going to first find two x-intercepts of the function x radical x plus 4. And we will try to look for a point C for which f prime is equal to 0. And hopefully that C is going to lie in between the two intercepts. And now we're trying to connect this to the Rolle's theorem. Before we hit the road, I want to show you the statement of the Rolle's theorem. Well, first of all, to be able to apply the Rolle's theorem, we should start with a continuous function f on the closed interval a and b. F should be differentiable on the open interval a and b. And for some reason, if we have the endpoints evaluated for f equal, then it's guaranteed that there is a number c in the open interval a and b such that f prime at c equals 0. So the secant line connecting the points f of a and f of b is horizontal. What that means is that the slope of the secant line is 0. And Rolle's theorem says that if you have that situation going on, then there should be a point within the interval a and b such that you have a horizontal tangent line. So you have the horizontal tangent line achieved like the secant line, which is horizontal, but within the interval a and b. So let's first try to look for the x-intercepts, and for that purpose, we're going to set f of x 0. So what that means is x times radical x plus 4 equals 0. Well, we have two different solutions here. One is obviously x equals 0 because that makes the equation 0. And another one is x equals negative 4. Okay? So these are the x-intercepts. And now we're looking for a number c in between these endpoints or x-intercepts. So in other words, is there any c such that c is in between negative 4 and 0? And f prime at c equals 0. All right, let's go ahead and find f prime. Well, we have the product of two functions here, so why don't we use the product rule for this function. So essentially it is the derivative of the first one, the first function in the list, times the second function, which is radical x plus 4, plus the first function times the derivative of the second function. So why don't we rewrite radical x plus 4 in terms of an exponential form so that we can use the power rule. So radical x plus 4 is in fact x plus 4 to the power of 1/2. And we take the derivative of this. And in the next step, we're going to use the power rule. The derivative of x is 1, so this becomes just x plus 4, radical x plus 4. And then we have x times the derivative of this term. As I said, you can either use the general power rule or the chain rule, all right? Either one. So the derivative of this is like 1/2. So x times 1/2 times the same exponent, but this time we're going to subtract 1 from the power. So it's going to be minus 1/2. And we're going to multiply this whole thing by the derivative of the inner function. But the derivative of x plus 4 is just 1, so it's just times 1. So to sum up, f prime is equal to radical x plus 4 plus x over 2 radical x plus 4. So I wrote this term as a radical term. It's a reciprocal. So it's 1 over x plus 4 to the power of 1. And to be able to set this to 0, maybe we should simplify this further. Why don't we put 1 here and find a common denominator. So the common denominator, in fact, is 2 times radical x plus 4. All right, after we multiply the top and the bottom by the common denominator, you have 2 times radical x plus 4 times radical x plus 4, which is 2 times x plus 4, which is 2x plus 8. And you have another x here, so in turn you have 2. All right, this is f prime. So we're looking for a c such that f prime at c is equal to 0. So let me just write that here. So, well, f prime at c is 3c plus 8 divided by 2 radical x plus 4. Let's set this to 0 and solve for c. And as you see, well, this is 0, but I can pretend like this is 0 over 1 so that I can do the cross product here. Okay, so one cross product gives you 3c plus 8. The other one gives you 0. So in other words, 3c plus 8 equals 0, implying that c equals negative 8 over 3. All right, this is good news because negative 8 over 3 comes from the interval for the x-intercepts. So in other words, we are having a horizontal tangent line at the point c equals negative 8 over 3. To check if the Rolle's theorem is applicable for this function, let's read out the statement of the Rolle's theorem again. So first of all, we should start with a continuous function, and then there should be an interval, closed interval provided to us. And I'm going to take the interval to be the interval made up by the x-intercepts. So the x-intercepts were negative 4 and 0. So why don't we start with this interval? So this is going to be my a, this is going to be my b. Let's first find a domain to start with. So if you look at the domain of this function, this is something from pre-calculus, so it's a good practice for us. So radical functions are only defined for x's for which, so the inner function is non-negative. So in other words, we're talking about x's for which x plus 4 is greater than or equal to 0. What that means is x is supposed to be greater than or equal to negative 4. The domain is negative 4 and infinity. Well, we have just x multiplying the radical x plus 4 within the domain of the function. F is continuous because if you want to graph this function, you're going to graph it without taking your hand on this interval. So f is continuous on negative 4 and 0. So f is continuous on negative 4 and 0. So the very first condition is satisfied. So the second condition is to check the differentiability. But we already came up with the derivative of f. And the derivative was, well, f prime is only defined whenever inside of the radical is positive, because we don't allow the bottom of this function to be 0, because then we're dividing by 0. So in other words, f prime is continuous, in other words, on the open interval negative 4 and 0. Okay, that's good because that's all we're looking for. The last thing to check is whether f of a equals f of b. Okay, let's check that real quick. That's just plugging in negative 4 for x, but you have radical 0, which is 0. So f of negative 4 is 0. Same as f of 0, because f of 0 is also equal to 0 times the radical 4, then it's 0. So also this condition is satisfied. F of 0 is exactly equal to f of negative 4. So all of the conditions up here are satisfied for this f, for a equals negative 4, b equals 0. Then it's guaranteed that there exists a c, right, in between negative 4 and 0, so the open interval negative 4 and 0, such that f prime of c is equal to 0. So Rolle's theorem only provides the existence of the c, the point c, but it doesn't tell you exactly what that point is. Okay, and in fact, we found that minus 8 over 3 is the root, so c here is, in fact, minus 8 over 3. All right, so we want to also verify this by this visual here. If we graph the given function on the interval -4 and 0, f attains the same value 0 at both points. So in other words, the secant line connecting these 2 points is horizontal. And a similar line happens, as you see, as a tangent line to the blue curve, which is this function, right? At the point of -8/3. So that's exactly what the Rolle's theorem said. The horizontal secant line is achieved somewhere in between the endpoints here, and in this particular case, the point is -8/3, and this visual confirms that. All right, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.